Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourselves ready with a notebook. Grab a pencil or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're continuing our discussion about sequences and series. Remember that a sequence is essentially a pattern defined by some kind of rule. It's like a list of numbers that has a pattern in it. So take a look at this pattern right in front of you. 1, 2, 4, 8, 16. I think you know where it goes from there. You understand what's happening to get to the next number. So today we're talking about geometric sequences and series. I have an interesting problem for you to think about, and it's about the game of chess. You don't have to know how to play chess for this. You just need to know that the chessboard, which is sort of the board that chess is played on, it is an 8x8 board. And apparently the invention of chess has its roots sometime in the past in Persia. And I want you to figure out how many grains of rice was this man awarded. That's the goal here. That's the challenge question. I have another question right over here, which is in this geometric sequence, some geometric sequence, 4 is the third term. Meanwhile, 125 over 2 is the sixth term. So here we have 4. And here we have 125 over 2. You could think of it also as 62.5. The question is, what is the formula for the nth term of the sequence? And then I want you to find A12. You can write your answer in a simplified fraction. So give yourself about 4 or 5 minutes to solve this problem, and then you can give yourself about 5 or 6 minutes to solve the challenge problem involving the chessboard. Go ahead and pause the video, take your time. If you need more time, that's okay, but try to speed it up here. When you're ready, you can unpause the video, come on back, and see how we did it here. Okay, getting started. So I want to show you the representation of terms in a sequence. Underneath, I have the index numbers. These are like the counting numbers. They're sort of like the pages on a book. They don't tell you what's on the page. They just sort of label the pages in order. They put them in order. And on top, of course, we have the actual value terms. And we usually call them A something. A1, A2, A3 just stands for their position in the order. Okay. Now, the ratio formula I could just give you, but I want you to really think about this. Let's go back to our sequence of 1, 2, 4. What is the ratio? In other words, what is being multiplied to get to the next term? Well, you can realize that that's being multiplied by 2 as we go. Wow, that was a bad arrow. You can realize that each of these terms is getting multiplied by 2 in order to get to the next one, right? So therefore the ratio is clearly 2. And I'm going to write it like this. AN equals AN minus 1 times R. Because in order to get to, for example, the fourth term, I have to come from the third term and multiply by R. So if we kind of rearrange this format, we can get a nice formula for, or a nice method for how to solve for the ratio each time. We can divide both sides by AN minus 1, and that tells us that the ratio is always simply equals to any number term divided by the number term before it. That's how you can find the ratio. All right, that's going to come in handy when we're solving our sequence problem. I also want to show you the general equation for the geometric sequence. This is the general equation for a term. an equals a1 times r to the n minus 1. If you think about it, this makes sense because from a3, I could start at a1, and then I can multiply by r to get to a2, and then I can multiply by r again to get to a3. Well, that's the same as saying a1 times r to the 2 power. So that's our n minus 1, right? This is our n equals 3, so this is our n minus 1 equals 2. All right, this is going to come in handy. I'm giving you these formulas. I'm not deriving them for you thoroughly. Just kind of showing you what they are. I'm not going to get into the logic too much, but I want to use them effectively. So let's take a look at an example here. If we start off with the number 3, this is our a1. It's our first term, just like you saw in the last video. First term is always a1. But as we progress, we have to multiply by r. So we need to figure out what is this r. Well, we can do that by saying r simply equals negative 1 divided by 3. How did I get that? Well, here is an, and here's an minus 1. I could have also done something more complicated. R equals 1/3 divided by negative 1. Or r equals negative 1/9 divided by 1/3. Any of these ratios, because I'm using the term and the term before it in all of these cases, that ratio is going to be exactly the same. Okay? So you can easily find your ratio. You can also just see it, right? To get to the next term, you can tell we're dividing by negative 3 each time. Okay, now let's tackle this question. In a geometric sequence, 4 is the third term, and 125 over 2 is the sixth term. What is the explicit formula for the nth term of the sequence? Well, we have to realize how many jumps occurred between the third term and the sixth term. That would be times r. That would be times r. And then again, we have times r. So what we could say here is we could say that 125 over 2 equals 4 times r cubed. Aha! And now we could find what the r value is. This is important because we cannot find the general term of a sequence without knowing the r value. Let's go ahead and divide both sides by 4, which is the same as multiplying by 1/4. And we get 125 over 8 equals r cubed. We're now ready to take a cube root of both sides, and these are perfect cubes. So the cube root of 125 and the cube root of 8, these are nice numbers. We just have 5 and 2. So this is the r value, but that doesn't fill out the entire geometric sequence. We need to find the nth term of the sequence. So here's how we do this. an equals a1. What is a1? We don't know what a1 is, which means now we need to take the 4 and go backwards and divide by r. So let's go ahead and do that. Let's do 4 divided by r squared, which equals 4 divided by 5 over 2 squared, which equals 4 divided by 25 over 4. And this is a pretty simple fraction here. We're going to get 16 over 25. So here's our a1. And then we complete the formula by saying the r value, which is 5/2 to the n minus 1. Nice. So finding the 12th term, it's not that easy. You might have to use a calculator, but if you can do this by hand, it's great. A12 is going to be 16 over 25 times 5 over 2 to the 12 minus 1. That's the 11th power. It's a high power. I don't know if we're going to be able to make it to the 11th power. But what I want you to notice is that if we do this a few times, it's specifically, if we do this 6 times, then we just have to do this 5 more times. Oh, whoops, other way around. If we do this 5 times, we just have to do this 6 more times. This gets us to the 6th term, which we already know is 125 over 2. Next, we would just have to multiply that by a rather massive number. If you don't know what 125 squared is off the top of your head, that's okay. I gotcha. I'm kidding. You should use a calculator if you really need to here. And so here we go. 125 is going to multiply to 15,625. Jeez, that's a big number, isn't it? It's something in the millions. It's like a million. Let's see, cut it in half, cut it in half, cut it in half. So that's 1,953. And then 625, cut it in half, cut it in half. That's going to be a 125 over 64. Goodness, this is a simplified fraction for the 12th term of the sequence. Kind of wild. All right, let's move on to the bonus question now. I did write out the geometric series formula, but let's reread the question. So the Shah of Persia, he offered the inventor of chess anything he wanted. And the inventor mentioned that he wanted to have grains of rice that go along with each space on the chessboard. He wanted 1 grain of rice for the first square, 2 grains of rice for the second square, 4 for the third square. So you see that pattern come up again that we started with, except now we're adding them because he's getting a total amount of rice for each square. So how do we add this up quickly? Well, we use this nice geometric series formula, which says that the sum of n terms is equal to the first term multiplied by the quantity 1 minus ratio to the n power divided by 1 minus r. Again, I'm not going to derive this for you. You can go look in a math textbook or go see the proof. I'm just showing you how it works here. I know that's not the norm, but I just want you to get through this so that you can memorize the formulas. You don't really need to make deep sense of them in order to use them effectively. So we need 64 squares. Holy mama. We're going to start off with 1, which is nice and small. However, this is quickly going to grow to be an insane amount of rice. In fact, 2 to the 64, I need to use Google for that. I do not even know what that comes out to. Can I see a full amount of what that is? I'm just curious here. I'm using some online software to get a number for that. It's approximately 18 quintillion, by the way, which is 18 billion billions. Goodness me. Let's put this number. Notice I did not tell you to do this one by hand. I would not have done that to you. This number is kind of insanely high. So the answer here is going to be 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, hi Elon Musk, 709,551,615 grains of rice. This is how much rice the man was owed. So I think it's safe to say that he probably didn't receive the amount. Most likely the Shah of Persia said, wait a minute. We don't have that much rice. In fact, we probably don't even grow that much rice in an entire year in Persia. It's just too much rice. 18 quintillion grains of rice. That is far too much rice. Who's going to count all of that rice to make sure he got the right amount? Anyway, this is a little coverage of the formulas you'll need for sequences and series. I think that's enough blab out of me. I'll see you guys next time.